This is Chapter 6, Circular Motion. And does a merry-go-round accelerate? A merry-go-round, even though it's going a constant speed, it will be accelerating because it's changing direction. So here's an athlete with, I guess you call it a hammer, and she swings it around in a horizontal circle and then lets it go so that it flies off into the field. So if we're looking down on her, she wants to let it go so that the hammer flies straight out to wherever the field measurement is. When we look at circular motion, what we're talking about is centripetal acceleration. And the acceleration always points towards the center of the circle. So think back to the athlete who was doing the hammer throw. As she swung around, a string was applying a force to the ball, and that is the direction of the acceleration. So centripetal acceleration, our formula is acceleration equals velocity squared over r, where r is the radius of the circle. If you need the time for one revolution, we call it tau. And so we often have things going in a circle, and to determine their velocity, we need to know their circumference. And you may remember that circumference is 2 pi r over tau, and that will give us our velocity. Once you calculate the velocity, you can insert that into your acceleration equation and calculate the centripetal acceleration. So v squared over r, if we substitute for v squared, you would calculate your velocity using 2 pi r over tau, and then insert that into your v squared over r. You may remember from Newton's second law that force equals mass times acceleration, and net force is the same as unbalanced force, which is the same as summation of forces, and that produces an acceleration on your mass. So let's look at our first example problem. We have a 13-gram rubber stopper, and it's attached to a 93 centimeter or 0.93 meter string, and the stopper is swung in a horizontal circle, making a revolution in 1.18 seconds. Find the tension exerted by the string on the stopper. So, on the next page, I'm going to list our variables. And we have a mass of 13 grams. We know it's attached to a 0.93 centimeter string, so that is our radius. And I said that incorrectly, 0.93 meters or 93 centimeters, and it takes 1.18 seconds to make one revolution. Find the tension exerted by the string on the stopper. So if your stopper is out here and the red line is your string, your free body diagram shows that the string is the only force acting on the stopper. So when we look at our summation of forces, we have summation of force equals ma. I'm going to put a C for centripetal, and our tension is equal to mass times centripetal acceleration. Now centripetal acceleration is v squared over r. So if I can figure out my velocity, I can solve for my force. So let's do that first. Remember, velocity in a circle is 2 pi r over tau. And we have 2 times pi, r was 0.93 meters, and tau is 1.18 seconds. Our velocity is 4.95 meters per second. Now, before I can use my equation that says the force of tension is equal to mv squared over r, I need to change my mass to kilograms. You need to divide by 1,000 to get to kilograms. So now, let's put in our numbers to calculate our force. We have 0.13 kilograms. Our velocity is 4.95 meters per second squared, all over our radius, which is 0.93 meters. Our units, when the units are squared, one of our meters cancels out and we're left with kilograms meters per second squared, which is a newton. The force is always a newton, and we have a force of 0.343. And there's the tension on the string. A non-existent force is something that some call centrifugal force. And if this car was on an icy road, it would just proceed straight off the road when friction didn't hold it to the road surface. Now, as you go around the path, centripetal acceleration is pulling the car inward, and that's being applied by the road to the tires. When your books slam against the car door, or you lean against the car door because you're on the outside or the passenger side, that is just the inertia of you traveling in a straight line until you get forced in the curve by your car. So another example, we have a runner moving at a speed of 8.8 meters per second, and that runner rounds the bend with a radius of 25 meters. What is the centripetal acceleration of the runner, and what agent exerts force on the runner? So I'm going to list our variables on the next page. And we want to know acceleration and what variable exerts the force, or what agent does. So this runner has a velocity of 8.8 meters per second, and the radius of the turn is 25 meters. And what's the centripetal acceleration? So if you remember, centripetal acceleration is v squared over r. We have 8.8 meters per second, quantity squared, divided by 25 meters. And our centripetal acceleration, 3.10 meters per second squared. Now, what agent is exerting this force? If you have a runner on the track, it's the track is exerting the force. So it's a frictional force. Let's look at another. This time we have a car racing on a flat track, and it's traveling at 22 meters per second around a curve with a 56 meter radius, and find the car's centripetal acceleration. So I'm going to put the answer up on the next page for you, but you do it yourself. Once you calculate, you should have 8.64 meters per second squared. I have one more example for you, and this time I want you to determine the minimum coefficient of static friction between the tires and the road necessary for the car to round the curve without slipping. So, we don't have any numbers, so we have to just look at it using our variables. And actually, this is the same car. I stand corrected that you just calculated the centripetal acceleration, 8.64 meters per second squared. So we do know that, so AC equals 8.64 meters per second squared. We do need to know that. So, minimum coefficient. Summation of forces on our car. Well, only friction's holding it to the road. And friction is U mg. Remember, it's the coefficient of friction times the normal force, and the normal force is equal to weight on a horizontal surface. And that's equal to m times a. Notice how your mass canceled, and your coefficient of friction is a divided by g. A is your 8.64 meters per second squared divided by 9.8 meters per second. And you have a coefficient of friction of 0.88 without any units on that variable. All right, that's it.